In the last video, we introduced the idea of logic as a way for human beings to communicate with computers, and we defined a proposition as a complete thought that has a definite and knowable truth value. In this video, we're going to look at how we can build complex logical propositions out of simple ones using logical connectives. Look at this basic recipe for peanut butter cookies. It's a list of instructions on how to combine the ingredients, and it ends with bake in a preheated 375 degrees Fahrenheit oven for about 10 minutes or until cookies begin to brown. Now, in some ways, this recipe is like an algorithm. It has input, instructions, and a definite ending point. What triggers the ending of the process in this case? It's not one, but two possible conditions. Either the cookies have baked for 10 minutes or they are turning brown. If I were a robot checking the doneness of these cookies, I'd have to monitor them and the clock and evaluate the truth values of two logical propositions. 10 minutes have passed, and the cookies are turning brown. If either one of these propositions becomes true, or if both of them are true, then I stop the cooking process. What that last condition in the recipe does then is connect two logical propositions with the word or, making a larger proposition. The word or here is an example of a connective, an English word that connects two smaller propositions to make that larger one. Sometimes we say that a proposition that cannot be broken down into a bunch of smaller ones is an atomic proposition. And a proposition that isn't atomic, that is, if it's made up of atomic statements joined by connectives, is sometimes called molecular. There's three basic forms of connectives that do this for us. So maybe we need some part of a computer program to activate if, like in this recipe, any one condition from a list of conditions is true. Again, as in the recipe, we usually use the English word or to connect the conditions. A statement created by joining two atomic propositions together with or is called a disjunction. And a disjunction is true whenever either one or both of the propositions that it joins is true. For example, either I passed algebra or I passed C++ is a disjunction. If you passed algebra but didn't pass C++, the disjunction is still true because the first proposition is true. You were telling the truth, in other words, when you claimed that you either passed one class or you passed the other. Same for if you didn't pass algebra but did pass C++. And if you passed both, the disjunction is still true, because if you passed both, then you definitely passed one. That makes our use of or into what we call an inclusive or. So the or statement is true if either one or both of the atomic propositions involved is true. The only way a disjunction can be false is if both statements involved are false. For example, if you did not pass either algebra or C++, the statement that you passed one or the other of them is false. One of the nice things about logic is that the content of the statements involved doesn't really matter, only the form. The truth value of a molecular statement, in other words, is always determined only by the truth values of the atomic statements that make it up and the connectives being used, and nothing else. For example, anytime you form a disjunction from two statements, the disjunction will be true if one or both of the statements involved is true, and the content of that statement does not come into play. This lets us summarize the condition where a complex statement will be true and where it will be false into a table, like this. Here, the V-looking symbol is a mathematical symbol used to represent the English word or. Different symbols represent or in different computer languages. For example, the double vertical bars represents or in Java and C++. In Python, you just type the word or. Since this disjunction involves two independent Boolean values, either of which is either true or false, it leads to four combinations of true-false values. In each case, the truth value of the disjunction is listed in the final column. As we saw, when either one or both of the basic propositions is true, then the disjunction is true. When both are false, the disjunction is false. This table is called a truth table, and we will be seeing much more of these in a minute and in other videos. Sometimes we need a part of a program to activate if all of the conditions in a list are true. For example, to take discrete math, sometimes you need a passing grade in both algebra and C++, not just one or the other. We use the word and a symbol that looks like an upside-down V to represent this connective, which we call a conjunction. In a conjunction of two propositions, both propositions must be true in order for the conjunction to be true. That's summed up in the truth table for conjunctions, which you see here. The conjunction is false otherwise. That is, whenever one or both of the atomic statements that make up the conjunction is false. And sometimes we need a part of a program to activate if a single proposition is not true. This is a connective called a negation, and we use this symbol to denote it. Negations are different than disjunctions or conjunctions because they only work on one statement. If you have the statement P, then not P, which is how we pronounce this, is its negation. The negation, not P, is true when P is false, and false when P is true. It's the logical opposite of the original statement. So in this video, you'll learn that we form complex logical statements out of atomic statements with connectives. We saw three basic connectives: or, disjunction, and conjunction, and not, negation. And we learned about the concept of a truth table, which allows us to see the truth values of a molecular statement as determined by the truth values of the atomic statements and by the connectives that join them. In the next video, we'll look at another connective, the conditional or if-then statement. See you there.